Hello everyone! In this video I want to show you the dynamic geometry software Cinderella. I'm using CindyJS for all of my videos, and it's a partner project of Cinderella, and I thought it might be interesting for some of you to learn how those programs work. But I won't do a, let's say, traditional tutorial where I go through all of the functionality, but I want to show you instead a couple of small concrete applications, how to do certain visualizations, certain little widgets you can use, for example, in the classroom. Today I want to focus on the geometry tools of Cinderella. The next video, which hopefully comes out in a couple of days, will be about the coding side of Cinderella more, and I plan to make those videos unscripted, fairly improvised, more like a live build of those applications. And hopefully that's interesting and educational and helps you get started with Cinderella and CindyJS. And now let's start. Now let's get into it, I guess. The Cinderella software itself you can get from Cinderella.de, and if you download it and open it up, it will look like this at the start. If we make the window a little bit larger, you see a bunch of different buttons here at the top. The first row has standard things like opening a new window, saving and loading, undo and redo. What we are mostly interested in is the second row. These are the geometry tools. There are many more under configuration choose toolbars. For example, there are some for physics simulations, which are very cool. But for us here, these default tools you see at the top, they are enough. And as I said, I won't go through all of them. Many of them are self-explanatory, and the documentation on the website is very good. I, as I already said, want to show you one little concrete application today, and it's more or less a follow-up to my first video on the channel. There I talked about how perspective drawings work, and in particular I used as the running example a perspective drawing of a tic-tac-toe grid. And the main insight in that video was that you can get, in a perspective drawing, you can get the middle point of a segment by constructing a square over it and then using the diagonals to cut the square into half. And that is preserved under perspective distortions, and you can use it in perspective drawings. I also showed how you can build up a perspective scale with this construction, which gets you very far but not everywhere. And this is what I want to do. Today I want to show you how to generalize this construction a little bit. What I want to end up with is this photo, and you can see here, let's make it a little bit larger. You can see here these rail tracks, they are parallel, more or less, hopefully, and they have these screws or pins in them. And if we assume that this pin here is at position 0, and this here at position 1, we have some sort of scale on this line here. And then I want to ask the question, and I want to show you the construction, that if you have any position here at, let's say, spot X and one at position Y, how we can construct the position X plus Y and the position X times Y, which means you can actually do arbitrary calculations inside of, in this case, a photo, or also inside of your own perspective drawings you might want to do. And to get started, I will look at the affine case first. So we think about what means to add two numbers on a normal affine line. To do so, I will start with a line, and you probably can't see the labels pretty well, so I quickly select everything, and with Control-I or Command-I you can get open the inspector, and here we can change the look of things, and if you go down one button you can get the default look of things. So we want to have label sizes of, let's say, 30 by default. Let's see if it works. Now all the new points also have big, easy to read labels. Okay, now what do we want to do? Let's say this is the point 0 on our line, and we also have two other points snapped to the line X and Y. And now we want to construct the point X plus Y. And you can do it in the following way, to take a parallel to the original line. And then you can construct a triangle over the 0x distance. And now we want to move this triangle over to the right. We can do that by taking parallels again. First for this side and then for this second side. And now I claim that this point here is actually the point x plus y. To see that this works, you can mark the triangles real quick. And the reason why it works is that these triangles are now congruent because of our construction. That means in particular the bottom edge has the same length. So if we here at position y, then the endpoint must be position x plus y. And the important insight now is that all we did is draw parallel lines and a bunch of connections and intersections. But the main ingredient was parallel lines. And in a perspective drawing, parallel lines do still exist. They are just not parallel anymore. They meet at a vanishing point, right? If you go to the rail tracks again, we can't see it directly because this point, which is infinitely far away, of course, doesn't really exist. But in the image space here, we have a vanishing point here. And all other parallel lines also meet at a point at infinity. And all those points at infinities, they lie at a line at infinity. In art class, you might call it the horizon. Technically, it's not really the horizon of the Earth. It's slightly above the horizon. But it's basically what you're thinking about. So here we have the horizon and all parallel lines meet there. And this way, we can generalize this construction here of these congruent triangles into perspective drawings. So let's get rid of everything and start anew. First we have our line. Let's get the inspector open again. This is again our starting point, 0. And now we assume that we have a second point which takes the role of the infinitely far away vanishing point. We can call it infinity if we want to, but the nice thing about Cinderella is that it can use LaTeX, so you can just write math expressions and math symbols into those labels. And yeah, let's leave it open, and we have again our 2 points x and y. And now we want to do this triangle construction again. So first of all, we need a parallel line to this number line we have. So this would be something like this, because it has to go through the same vanishing point. Now we do our triangle again, which looks like this. So let's move everything a little bit down to have more space. And what we now need is, well, the vanishing points of these two lines, because we want to make parallels for those. The vanishing points for those lines lie on the horizon. And now we can just use an arbitrary horizon. I will take this one and make it purple to mark it as special. And it really doesn't matter which line you used as the horizon for this, because at the end we are only interested in what happens on this line here. And it doesn't have to be the horizon of the actual photo, of the actual drawing, but if you have that, fine. If not, you can just take anything else. And now we can do our construction again. So let's move it a little bit here. And well, first we need the parallel to this line here. So it has to have the same vanishing point, and it goes through y, the second point. And now we need a parallel for this line, means this vanishing point, and we want to complete our triangle. And now I claim that this is x plus y. X plus y. And we can also mark the triangles again, of course. They don't look congruent, of course, because we're now in a perspective drawing. But since we replaced being parallel by meets at a point at infinity, this will work out. So this is the perspective version of what we just had. And well, yeah, now we want to compare it to our photo, or maybe before we go to the photo itself, let's quickly make a sanity check that it works out. So for example, if we take x to 0, x plus y ends up at y, which makes sense. And if we move x to infinity, x plus y ends up at infinity too. So that is believable. And you also see that here at this very point, the construction itself technically doesn't work anymore, but Cinderella has some nice numerical resolutions for those singularities, so you can move through those special cases without worry. And yeah, now we want to get to the photo. Let's erase our triangles again and get the photo into Cinderella. To do so, we go to the File Manager, the media browser. I always call it File Manager. And we load the file. I think it's somewhere here in my download folder. And now it is there. We can rename it. The standard name or the default name is the file name, which in this case is very long. So let's call it image0. And now let's draw it. For that, we have to do a little bit of coding. So we go to the script editor here. And in the next video, I will show you and explain you in detail what all this here means. For now, For now, all we need is the draw script, because we want to draw an image, and we draw image. And now we need the position and the name, and I always mix it up, but I think it's the position first. Let's take the origin and the image name, which is image0. After you did some coding and you want to see the changes, you click on this gear symbol here. And if we do so, we see the image pop up. All right, so close the script, and that is all of the coding we will be doing today. So let's move those points somewhere to those screws. Well, first of all, it's hard to see on this very dark, grayish orange image. So let's take everything and make, let's make the lines, the points a little bit larger, the lines a little bit larger. Let's make the main number line. So we take these points, we make them, black, and this line we make white. We make all labels white, which is somewhere else, which is here, I think. Make the labels white. Now it should work, yes. And now we can see it a lot better. And let's make this auxiliary construction here. First of all, remove the labels and make the lines and points, orange maybe. Maybe that is nice. And we can also shorten the lines a little bit. So now it's a little bit more confined. The final point should also be black, and maybe the result orange. Does this now look nice? I think, right? If we use the net here, we can focus on everything we have, and now we can try to align this with our screws on the photo. To do so, we would now need to find the vanishing point and place it there. And we already talked about this. It doesn't really show on this image, so let's construct it. Let's draw new lines. Let's draw one line, let's say here, and one line here. And now this resulting point here must be the vanishing point. And let's make it a little bit cleaner. Let's zoom in. Let's place it properly. And this one. And let's focus everything. And here is the next one. This might be the middle. And maybe here. Is that good enough? I guess. And now if we zoom in, well, you already see those tracks, they go a little bit to the left, so they're not perfectly straight. But if we assume that we continued the first straight path, the first straight part of the rail tracks. It works out, I think. And now I hope this works. We can snap this point at infinity to this point, and now it's gone. It got absorbed by B, and we can place 0 here. It also got absorbed. So let's quickly, I just wiggled it. So let's take this point. So first of all, we pin it so it can't be moved anymore, and then we relabel it again. The same thing here. Add the label again. And well, those points we can also pin it, first of all, but moreover we don't need them anymore, so we hide them. We make them invisible, and this point too, pinned and invisible. And if we want to go back to them for whatever reason, we can use this spotlight here. Now it shows up really bad here, but maybe you can see it. If I toggle it a couple of times, we get back to the hidden objects. And we also have this helper point here, right? So make it pinned and invisible, and now nothing can happen anymore. And now hopefully our construction works properly. So we set up one point at 0 and use, that point could be a little bit larger. And that point could be a little bit larger. Maybe something like this. All right, let's get back to our construction and see whether it works. If we place the first point x at screw or pin number 1 and y at the same point, we get x plus y equals 2, which makes sense. If you place y at 2, we get the third screw as the result. And if you use something more, let's say, what is this now? This is 1, 2, 3 for x, 5 for y, and now this is 5, 6, 7, 8 for x plus y. Seems to work. And if we zoom in, again up to actual not straight rail tracks, and of course a couple of placement errors on my side, it works out pretty well. We hit the screw. Maybe not in the center, but we hit it. And well, this is a way how you can construct the sum of two perspectively drawn numbers on a perspective scale. What you can also do is, let's get to the polygon tool again. If you mark this quadrangle here, you can see how the structure works. You can, let's say, take the left and right side of this quadrangle. They meet the number line in our input variables. The bottom and top, they meet at infinity. So the top one was, if you remember that, or if you go back to it, the top one was the horizon and the bottom one was a helper line. They meet at infinity. And the diagonals, well, one of them goes through 0, which is the neutral element of the addition, and the other diagonal hits the number line in the result. In this way, I always remember it. Maybe not the best way to remember it. The original construction I showed you is probably the better way, but this is the way I always remember it in the perspective case. And well, I already told you that we want to do the same for multiplication, and it turns out it more or less is the same construction, just slightly different. So let's delete this for a moment, move this construction, let's say, down here and make it invisible for now and the result invisible. And yeah, now we have our setup for multiplication. And before we do it on the photo in the railway tracks, I want to explain it to you somewhere else. So let's move somewhere else. If we have our number line, let's make it a little bit more horizontal and a couple of points. Let's assume at the start we have 0. We have the point 1 because we want to multiply, so we need that one too. And we have again x and y. We make a very similar construction. We start with a helper line, which is now going through 0. And now we start with a triangle again. This triangle will now be at 1x. And now we do very similar thing. So we start with a parallel line. So maybe mark the triangle first. So we are talking about this triangle. And now we want to scale it up. We do that by a parallel here, which run through y. And then we need this intersection. Let's make it maybe like this. So we have this parallel. So these are parallel, and now we have a second parallel here. And now I claim that this is the result x times y. Again, we have our second triangle. And the reason it works now is not that they are congruent, but they are similar because we just scaled it up. And because now, well, this distance here is now a factor of x, and then we scale it up, we get a factor of x for the second part, and this means this whole segment will be x times y, because these triangles are similar. And just as before, all we did was, well, connecting and intersecting a couple of things, but mostly parallel lines. And this now carries over, of course, exactly the same as before. So we can remove that. Let's focus what we already have. And now we need the 1 point here. Let's zoom in, make it black again for consistency. Maybe here. That looks nice. It also sounds nice, I guess, but yeah, let's do the same construction. So we started with, let's get rid of the inspector. We started with a helper line here. Oh, first of all, let me quickly pin this before I forget it and make it larger too. Okay, now we can start with this helper line we had. And now our triangle. And now it's already hard to see. Let's make it a little bit easier to see. So let's change the default behavior again, slightly larger points, slightly larger lines, and make the lines endpoints, I guess, blue for the second one. Do we need this point? Probably should have used it somehow, but doesn't matter. So this is our triangle, just to keep track. This is the triangle we want to scale up now. So we need a horizon again. And just as before, we can use any line because we are only interested in what happens on this number line, this white one. So we can take that. And now the parallel to this left edge will be this one. Yes, it has to go through y. And now we need a parallel for the right edge through this point. And now I claim that this is, in fact, the perspective x times y. And where is it? Here is the scaled up triangle. And again, it doesn't look scaled up anymore because it is now the perspective version of what we had. But if you compare this structure to what we had before, it is exactly the same. Again, all we did is replace parallel by meets at a point in infinity. So let's delete those again, and yeah, let's make this helper construction a little bit nicer. Remove the labels, shorten the lines, and yeah, as I said, this point here is probably it's not well placed. I should have removed it, but not so important at the moment. And now we can check whether it works. So let's first of all make the obvious ones. So if x is equal to 1, x times y will hit y. If x is 0, x times y is 0. And if x is infinity, x times y is infinity. So it seems to work, but let's do some numerical tests. If you place x at 3 and y at 6, is this right? 1, 2, 3. 4, 5, 6. The result should be at 18, Let's check. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Looks about right. And let's see how well we hit the screw. Well, not particularly well, but then again, as I said, the rail tracks aren't perfectly straight in the photo, and I probably haven't placed the original points perfectly. But it more or less checks out, I guess. But I hope at least you believe me that this construction now works. And well, the last thing to do is look for this quadrangle. If you look at this quadrangle again, we have the same structure as before. Let's move it here. Maybe like this. Maybe this is nice to see. So again, the vertical lines, the left and right sides of this quadrangle, meet the number line in x and y, the input values. The top and bottom are again the horizon, the line at infinity, and our helper line. The helper line now runs through 0. And the diagonals, once again, are the result and the neutral element of our operation of 1. So it's more or less the same structure, just slightly different setup. So we need this additional point 1, and this helper line runs somewhere else. So let's get, let's keep this, let's make it maybe blue, then you can compare it a little bit better, and let's make it visible, but like see-through. And now, where is our original addition? Let's make that visible again, and make it larger a little bit, and now we can compare it to this quadrangle 2. Let's make it orange, and now you can see and compare the similar structure. Oh yeah, that point. Make it similar to. And yeah, that's the idea of how to do calculations inside of perspective drawings and inside of photographs. You can use it, for example, to measure things in photographs if you place the points well enough. And I hope this was a nice introduction, or a nice first introduction to Cinderella. As I said, unscripted, probably very minimal editing. And in the end, maybe it was helpful to you, at least interesting. Next video will be about coding. And if you enjoyed this video, let me know in the comments. Let me know what kind of constructions, especially geometric constructions, you would like to see in Cinderella. And I will do these kind of videos every now and then. The last thing to say is that I will put the Cinderella file, which I just constructed, into a GitHub repository, which is linked down below in the description. And with that, thank you for watching, and until next time.